Edward Moses is an American physicist internationally recognized in laser and optical sciences and is the current Principal Associate Director for the National Ignition Facility and Photon Science Directorate, the largest experimental science facility in the U.S. and the world's most energetic laser, that hopes to demonstrate the first feasible example of usable nuclear fusion. He holds several patents in laser technology, fusion and fission energy, and computational physics. Dr. Moses is a member of the National Academy of Engineering and a Fellow of SPIE and the American Association for the Advancement of Science. He received a BS and PhD, both in electrical engineering, from Cornell University.
Please welcome Dr. Ed Moses.
Good evening. I'm going to talk about something a little bit different. I'm going to be talking to you about fusion energy. I think it's the coolest form of energy in the universe. And I also am going to talk to you about how we do it using lasers. And because of that, we call it laser fusion energy, or LIFE for short. And I think it could change everything. And hopefully I'm not the only one who thinks that. Recently, Steve Hawking, who's a famous physicist, a famous thinker, philosopher, was asked what is the most important scientific or technological advancement that he would like to see in his lifetime. And he said he would like to see fusion energy made practical because it's inexhaustible, it's carbon-free, and it would change the whole view of global climate warming. What more could you ask for? But one of the problems is few people know what fusion energy is. And when we talk about fusion energy, we don't mean nuclear fission energy or nuclear energy as we have when uranium nuclei are split apart. We get energy out, we get some other stuff we might not like to get out. We're talking about nuclear fusion, where we actually take the nuclei of hydrogen, as in water, put them together at high speeds, at high temperatures, get out all this energy, and without having the byproducts that we don't like. And the thing that I really like about fusion energy, besides that it's so clean and cool, is here's another view of the Hubble Deep Field Space Telescope that Alex was showing you, except when I see it, I don't see the universe expanding. I don't see dark energy and dark matter. I see billions and billions of galaxies that are burning hydrogen in a fusion way. And every single photon of light that we get from space, whether it's night or day, comes from fusion. And fusion is the natural source of energy of the universe. It powers our universe. It's clean. It's reliable. Every day in every way, you know the sun's going to shine. And this is what we want to do in our field. And the question is, if it's so good, why don't we have it? Could we find a way to build a miniature star on the Earth? One that we could use to power our civilization's future? And the answer is, I think we can, and I'm going to be talking to you about that in the next 15 minutes and 25 seconds. And when we get through with it, I hope it'll change your collective future of the possibilities that we face. This is the NIF. It's at Lawrence Livermore National Laboratory, just east of San Francisco and south of San Francisco. It's the world's most energetic laser. This is where we're trying to build a miniature sun. So before we go on to that, I want to talk about the energy problem. You know, when we look at this picture, we can see a lot of things. You know, this is the hydrocarbon world we live in. We're looking at a coal-fired power plant. It's putting out enough energy for a little bit more than San Francisco. But the fact of the matter, when I look at this, I don't see an energy problem. There's a lot of coal in the world. This is the problem. You know, when people talk about energy, it's really the three E's: energy, economy, and environment. You got to put that all together in order to understand the problems we face and the solutions we deal with. If you look at coal, we have enough to last forever, and forever is hundreds of years. If you look at it in the context of the environment, it changes your view of everything. If you look at oil in the context of the economy, it changes your view of everything. We have to think about this as a troika that we find a common solution to. You know, energy fingerprint of humankind really shows up in this famous NASA picture, but again, I think it's slightly misleading. When you look at this, you see, you know, the United States and Europe lit up really well. You see India looks pretty well lit up, so does certain parts of China. But the fact of the matter is that the energy intensity of both India and China, big population centers, over 2 billion people, is probably 10 or 15% per capita of what we use. When you look at Africa, you only feel fear, right? There's nothing. Those people are coming on board and want to have a better standard of living. And the way they're getting it is building coal-fired power plants. In fact, right now, about 100 big coal-fired power plants per year are being built worldwide. That's a pretty scary thing when you think about it. So that's where we're going, and what we're concerned about is the environmental part. When we look at this picture, people talk about the oceans, they talk about the ice caps, they talk about warming. This is sort of a situation that's really reaching a critical tipping point. Most scientists think that in the next 40 years, we have to remove most of the carbon that we now have. In fact, some people even say we have to go to pre-industrial revolution carbon emissions. That's a huge problem when you think ahead to 9 billion people. What are the solutions that people propose? People propose carbon-free things like hydroelectrics, renewable energy, nuclear energy, some pretty hard things to do, carbon sequestration, where you actually take carbon out of the atmosphere, out of the flues that we are burning it, make it liquid, pump it back underground, keep it there for a while. They also talk about low-impact lifestyles, energy efficiency. The fact of the matter is, when you put these all together, as a scientist, as an engineer, these don't cut the cake for everyone, everything that's going on. They'll be a part of the solution, but they're not going to be a whole solution. So the question is, what are we supposed to do? Now, I think our city is a great example, the city of San Francisco, of the problems that the world faces. It's a small city. It's about 1 million people. It's fairly energy intense, but it's more and more a typical city. As people move to cities all over the world, populations of 1 to 3 million, like the Bay Area, are growing and growing. And you have to realize we're a carbon-based city. So the question is, if we stay here, where is it going to go? And when I look at this, I want to try to remove the boundaries of our imaginations of our future and think about another possible solution. One in which, we would power this city for a year, 1 million of us, with 150 gallons of water as fuel. Most of us spend around 200 gallons a day on water. Okay, what about if the waste product was helium? And for the whole city, we've made about 1,000 toy balloons of helium as our waste product. What if this power plant could fit in a building the size of Costco? And what if we built one of these, we could put them everywhere? So they could be local, they'd be safe, they'd be capable of changing sort of the equation in a fundamental way. This is what we're trying to do with the NIF. And this target that I'm showing you here, and I don't know if you can see it because it's so small, that I'm holding up, is the miniature sun that we would like to build that would do everything I just said. Now, we need more than one at a time, but I'll show you how we do that in a long time. So this is the goal of our thing, to get fusion in the laboratory and then make it a part of our commercial world. So one of the things I wanted to talk about is, what does the NIF look like? So this is kind of a different thing. The NIF is a really big facility. Let's see if this comes up. Yeah. Hey, let's have a round of applause there. So when I go to the NIF, I always feel small. I feel small by the idea, and I feel small by the facility. And now I feel small at being in this planetarium. But that's what the NIF looks like. So this is not a cartoon. This really exists. And if you go inside, this is one of the laser bays. And these laser bays are kind of interesting. If you look over there, you can see one end and go wrapping around and see the other. This is around 400 feet long, which is a little bit smaller than this dome. And we have 192 laser beams, and they all go to this target chamber. This target chamber is around 35 feet in diameter, and you can see those beams. I just think this is so amazing from where I'm standing. Anyway, it's actually better than real life. Anyway, coming down into the target chamber, and if you go inside the target chamber, this is what it looks like, right? And you can see at the end of that arm, and left and right don't mean a lot in this place. You can see where that target is held. So it's a big facility, and that tiny little target that we just looked at is in it. And the laser beams, all 192, come onto it, and they heat this up to very high temperatures and very high pressures and make this happen. So let's go back to real life here, come back to me. How did this all work? We already talked. Alex, again, beat me to Albert. Albert told us that there's a great equation, his most famous equation, equals mc squared, that energy and mass are sort of the same, and you can change one into the other with this little constant called the speed of light. It's a really big number. The way to interpret this is small amounts of mass can really result in large amounts of energy. So the purpose of a fusion system is to use those lasers to change a little mass into more energy. And that way we can get more energy out than we started with and have sort of a neat machine. We know it works. If we go to the sun, we go inside the sun is a big ball of hot hydrogen gas. If we go inside of it, we see hydrogen nuclei smashing together, fusing, making energy, putting out photons. We call those photons sunlight. They come out to Earth. They provide the source of all power that we have and all life that we have. Sort of the natural thing. As I said, it's all the time it's going on. So what can we do to build a miniature sun on Earth? And this is how we think about doing it. This is actually another view of the target chamber. And here we see that target right in the center of the target chamber, a big building. These targets, again, sort of the size of a Tylenol pill. And we can hit these targets within a few trillionths of a second and less than half the diameter of your air. So this is a really precision machine. And even though our ant guy said he can take high-speed motion pictures at tens of thousands of frames a second, we literally take them at billions of frames per second because things happen fast. And this is sort of how it looks when it lights up. And now I'm going to show you a picture, an animation that brings this all together. So this is real life. Do we have a little sound here? This is real life. And
4,
not that much.
3.
Okay, this is a countdown.
2, 1, shot.
And now we can see an animation of what's going on. Happens in real life. Here's the voice of NIF. It's the master oscillator room where a small amount of energy comes out that has all the information you need to implode a target, but not enough power to do it. So we go out to our preamplifiers. Remember, 192 beams. It actually plays music as it goes. So here we have this chunk of light that's about 6 meters long, 20 feet long in your language, right? And it's going back and forth through the laser beams. It actually would look like this if you took a movie of it, and it's getting more and more powerful. And those 8 beams, which we call a bundle, are the Lego block of NIF. But we need a lot more of them, so you watch what happens, and now some cousins are going to come along. Now we look at a cluster of beams, and we have 48. And now another side of the family is going to join up. So we now have 96 beams. This is going on the other side of the facility too. We go into this big optical mirror machine that makes it from 2D to 3D. We got to time all these beams up, so watch how they time up. They're in the infrared. Now they're timed up. Now they're turned ultraviolet, and now they go on to a target. Now we're about to build our sun. A millionth of a second has gone by. 1 millionth. Now you watch the billionth of a second go by. We have this little oven, that target. We heat it up to millions of degrees. No, that energy is now onto that hydrogen ball. It goes up to hundreds of millions of degrees. And now we have a sun on Earth. I think that's cool. Okay. So the question is this safe? Is it sane? Is it sound, right? And the answer is yeah. I mean, we are burning hydrogen. We're burning hydrogen in a different way than chemical way, about 30 million times more energy. It's over in a few trillionths of a second. Once it starts burning, a few trillionths of a second, you burn all the fuel, it stops. So it's the kind of thing we like. The question is, how would you do it commercially? Right? That's a one-off machine. What's really cool, it's always one-off. This is a view of the Life power plant. Now here we see a 1 hertz machine, or 1 times a second. And you can see that the target comes in, the laser hits it just like in the NIF. We haven't built this one yet. And we get energy out. I'll tell you how we capture that in a second. Now we do it at 10 hertz. Does anyone know what 10 hertz is in normal language? 10 times a second, or 600 RPM. So what is your car idle at? Around 600 to 800 RPM. So that's just a 1.5 million horsepower engine, no carbon, right? Kind of cool. The only thing you're burning is the hydrogen in water. And when you stop, the question is, well, what do you do now? You got all this high-tech, highfalutin physics going on, but how do you make electricity? And the answer is kind of disappointing. You know, we absorb that energy into this salt blanket. That salt blanket we pump past some hot water. We make steam. We turn a turbine. We make electricity. It's a little embarrassing at the end, but that's but that's exactly what you want, right? Because now you don't have to invent new grids or new anything. You just use what we got, right? So when you plug in, you know, your hair dryer or whatever you're going to plug in, you know, you can't tell that it came from fusion. It's just normal electricity. The only difference is when you go outside, you don't have any pollution, and you don't have any global climate, and you don't have to worry about where your energy is coming from. I like that idea. So what's our plan for the, let me just see something. Did I do this? Yeah, so, you know, when I think about this, I think about what's the future look like. You know, I'd like to have a planet that had clean air. I'd like to have a planet that had clean water. I'd like to get rid of those political tensions that come with energy. You know, I think this could be lived to a world that is happier and, you know, to quote Sandra Bullock, you know, and world peace. Remember that movie. And I think that this is possible using life. And life is the way we'd like to do it. We'd like to invent the future together. The question is it possible to do this in the time scale that we talk about? You know, our goal, our roadmap is 2010, you know, into 2012 to get this ignition, scientific feasibility. I want you to know we're doing experiments every day that are very, very encouraging. You know, 2020-ish to do an engineering prototype, 2030 to be commercial. Now, you can't do this on your own. We've been talking to the utilities all over the country, actually all over the world, who are very interested in this. They're helping us understand customers' needs. We're talking to Silicon Valley and heavy industry with the power industry, so we make the best business model. And we're also talking to a lot of environmental groups who have been extremely encouraging with respect to our future. If we get online by 2030, we're just at the time we need to be in order to make this all play together for our challenge. You know, by 2050, our goal would be to be a significant part of the carbon-free future. So if you want to visit us, you can have 2 ways. You can go to lasers.llnl.gov. We have a lot of information there. If you want to come out and see us, believe it or not, you can call up our public affairs office. We have tours all the time, and we'd love to have you there. I assure you, it's better in 3D than in 2D, even up there, even though I'm not sure anymore. Anyway, and you know, we'd love to have you, and it's been my pleasure giving you this talk. Thank you so much.